On today's episode of Good Idea, Bad Idea, alkaline batteries. Should you recharge them? No, definitely not. Let's do it anyway. A simple, non-rechargeable, so to speak, alkaline battery is the simplest, smoothest, in my opinion, nicest form of energy on the planet for electronics. It is a two-terminal device. It has a positive and negative end. The long ones have a little nubbin that's the positive end, and this one's the negative, the flat part. Same for the little ones. The 9-volt batteries have two terminals on top, one larger than the other. There's a symbol that says positive and negative on the side of the battery, and in this case, the smaller terminal on the top is labeled positive. And then, of course, you have what we call coin cell batteries. The coin cell battery has a terminal on the top and the bottom. And you might think, well, it's all metal. How does it separate them? There is a thin little, insulated material, gel, whatever it is, ring on the bottom to separate the bottom from the top and sides, because the top and sides are essentially the positive terminal. And the positive terminal is the top, which, that's not clear, but it's written, and it has a little plus on it, so the side with the writing on it is the positive terminal. Here in the States, we call them D-size, C, AA, AAA, 9-volt, coin cell. I assume that is somewhat international. I have no idea. I'm sure you can figure out what they're called wherever you're from. The actual construction of an alkaline battery is very simple. You have chemicals inside that cause a reaction. I won't explain the chemistry. That's for a more expansive time. But see the plus and negative end. So the chemistry causes an imbalance of charge. On the negative side, there's a buildup of electrons. They don't want to build up because they want to all spread out nice and even, but the chemistry forces them over to the negative side from the positive side. So the positive side lacks electrons it really wants because it wants to be nice and even once again. So you have a positive charge on the positive side, negative charge on the negative side. This is your voltage. Voltage is just a difference in charge. Now what happens is when you connect this to a circuit, the electric field spreads and current flows. Now it's an almost universally bad idea to connect power supplies together in any way unless they are specifically designed for it. Some of them are, look on your manual, but batteries are really the only time you should. Because batteries are nice and modular, and they're nice and even and smooth, and you can put them in little packs all together. Whereas if you have like a wall wart or a generator or something, you can link together generators with governors and sync them up and all this other stuff. And there are switching power supplies that are designed to be run together. But overall, if you need more voltage or more current out of something that's not a battery, just get a different power supply. Get more windings in your transformer, or fewer, or something like that. But batteries, it's very nice because you can have essentially one size fits all. You've got your 1.5 volt, and then you've got little ones and big ones that have different amounts of energy in them that can supply different amounts of current. You can combine them. You've got your 9-volt that has more volts. It's just nice to put them together like Legos. So you can put them together. And the reason that it doesn't immediately catch fire is because you have the positive terminal of one battery connected to the negative terminal of the other. All right? And what's happening, not right now because there's no circuit, but what would happen if this was connected to a circuit is negative charge, the electrons from the negative terminal of this battery, would travel just to the other side and connect to the positive terminal of this battery. They're not going through the batteries. So essentially the circuit, you've got your negative end over here that's pushing electrons out all the way through the circuit. The electric field is doing it, you know what I mean. Pushing it through the circuit into the positive end here. But in order for a circuit to be connected, it has to be connected here too. So there's a push of the electrons into this, which then equalizes and pushes some electrons out of this end into this one, which equalizes, pushes electrons out on this end, and the cycle continues. So that is why you can connect them in series without even a thought. But the point of this is recharging. Everyone always says, don't recharge them. The manual says, don't recharge them. The manual is right. So there's two things going on here. First of all, if you apply current in reverse, if you put in the battery backwards, it's going to try and charge. and it will charge. The thing is, only some of the chemistry is reversible. Chemistry is just you have molecules and they become other molecules. Sometimes you have heat in, sometimes you have heat out. That's called endothermic and exothermic for fun. But the point is, you just have molecules converting to other molecules for the most part. And in a battery, there's very little heat generated, so pretty much that's what it is. So if you hook it up backwards, you charge it, you're forcing those chemical reactions to run in reverse. But only some of them can. Some of them can't. That's why if you charge it, you're not going to get back to full capacity. Only some of them will. You'll get some charge, not a whole lot. And every time you do it, you drain it, charge it, drain it, charge it. Maximum life is degraded because some of those chemical reactions don't go back. In addition, there is gas. I believe it's hydrogen. I don't actually recall, but there's gas that's generated. So have you ever seen one of these batteries that is all out the end? Little white powder all over you, chemicals? That is the gas that has been built up and it has burst the ends. Charging backwards generates a lot of this gas. Just sitting there, some of the gas is generated. Normally, over the course of the lifetime of a normal battery, this is not going to become a problem because this is a nice tight package and not enough gas is going to be generated to do anything. But if you are leaving it in a drawer for 10 years, or like me, leaving it in a Wiimote for a number of years, trying to open that Wiimote battery pack later and having to then clean chemicals out of that for 10 minutes, or you're charging it, then it's quite possible your battery explode. But if you're careful, it won't. So let's try it. So for the sake of demonstration, I have taped some wires onto the end of a 1.5 volt AA battery. This thing will supply a couple amps if you wanted to. We're not going to try and do that. So I am now going to connect this battery into my breadboard. You don't actually need the breadboard, but you really should have one just to make your life a whole lot easier. I have taped wires onto this battery. Make sure that the wire is on the positive little nubbin, and look for the nubbin so you remember which side is positive because you've now covered it up with electrical tape. I will now connect it. The positive, once again, look for the nubbin. We'll put in a nice positive trace here, the negative into a negative trace. I will now use my multimeter to measure the voltage. Let's put it on 2 volts because that is the maximum we need to measure. So the positive lead of the multimeter into the positive, negative into the negative, and I have done it wrong. What did I do? There we are. There was just a loose wire somewhere, and it is fluctuating like mad right now. Oh, there we go. Let me try putting these in different traces. Oh, massive fluctuations. So this is a sign that your wires have gone silly. These wires are nice and wonderful, but they're also delicate because they are just soldered, and I have a habit of pulling them out by the wire instead of the connector. So this is not going to work. So let me try quickly making another one. I have electrical tape, and I have scissors, and I will show you how to do this in another video. This is just quickly for me to get this running right now. So we tape down the negative terminal, or attempt to. This really is a pain, and I'm only doing this for a demonstration. This is not for daily use. There we are. That should hold the negative. And now the one that's actually annoying, the positive terminal. I've taken way too much tape. Good thing the entire roll costs $1. So let's make sure I do this correctly. Let's put the wire in the same rough place coming out, onto the little positive nubbin. Squeeze it down if I can. Seems to be on there. And now I will check my handiwork and make sure that it is not also silly. The positive end is over here. So positive, negative, positive, negative. And now it is nice and stable and wonderful. Hopefully you can see that. 1.598 volts. This is an approximate reading. Everything everywhere is approximate. That's why we have error bars. So this battery is 1.598 volts roughly right now. That is about where it should be because it is designed to be a 1.5 volt battery. According to the internet, you should not charge a battery more than a little bit above, such as a 1.5 volt battery should be charged to no more than 1.65 volts. That's fine. We're only going to charge it enough to show that it's being charged. That is all. So I'll take the meter back out, set that on the side. And now I will use my bench power supply to actually charge it. So there are circuits on the internet that you can look at that have indicator lights and current regulation, switching, linear voltage regulation, auto shut off, all kinds of fancy stuff. Even ones that alternate charge on and charge off to reduce the chance of your battery exploding. Don't do any of that. Like, I mean, if you want to do it for fun, do it for fun. Like, fun is good. Do it for fun. But if you're trying to actually do this for recycling, don't, because actually recycle your batteries is a better idea. The better idea than that is just get rechargeables. They're designed for this. It is not economical. Like, you spend so much time and energy and money making these chargers or buying these chargers to top off your alkalines. It's pennies on the dollar you're saving. You are saving money, but it's pennies. It's pennies. Get rechargeables. Just do it. But this is for fun, so let's have fun. And one important thing, because the batteries can explode, I am using eye protection. Hello there. Now, eyeglasses are not proper lab eye protection, but you don't need proper lab eye protection here because the chemicals are not dangerous if you just wash them off right away. The only time it's dangerous is if you get them in your eyes because guess what? Your eyes are wet. So it will immediately start reacting with your eyes and cause problems. Anywhere else on your body, all you do is stop what you're doing, go in the bathroom, and rinse them off. So I will now hook the power supply up. Remember to have your current set at 0 amps so that it does not try to supply charge right away. I have mine set at 12 volts. According to the internet, it just needs to be at least 6 volts above the thing you're trying to charge because it has voltage. And you have to counter that voltage and then push it in. You're basically swimming upstream. So you have to have a nice big push. But we have current limitation to make sure that it doesn't push too much. So that will be fine. So remember, we are hooking this backwards. So the positive of the power supply is going to the positive of the battery. And the negative of the power supply is going to the negative of the battery. And as soon as I do this, something's going to happen. But I have it set on 0 amps, you say. What could happen? Watch this. It's still 0 amps. There is no current. There's effectively no current. There's a teeny tiny trickle. But there's effectively 0 amps, no current flowing through this circuit right now. 1.55 is pretty close to the voltage it's supposed to have, isn't it? It's actually countering. See, it wants to put out 0 amps because that's what I told it to. To do that, it has to have some voltage to push against the voltage the battery is doing in reverse. If you have hooked this up wrong, then you will know. I haven't tried because I don't know if it's going to destroy my power supply or not. Try to not do things wrong. But the point is, this is hooked up correctly, and it's outputting enough voltage to exactly counter what's going on. So now, if you observe, I'll turn it up a little bit, and you see the voltage is going up. So it's how much it has to counter plus a little bit. So right now, it's putting in a net 5 milliamps through the battery in reverse. So let's speed this up. We're going to turn it up to 50. That's 50. And we're going to wait a minute. So you can see 1.62 volts. So 1.5, let's say 1.55 it showed. That's 5.7, so 7, so it's 1.62, so that's 70 millivolts. 70 millivolts over the voltage already in the battery. Now, this isn't going to take long. I'm not trying to charge the battery fully or to a specific point. I just want to charge it to show it charged. So you check. There should be no significant heat, no significant bubbling. Nothing seems to be happening other than the obvious. And I believe that will probably do it. Again, I'm only trying to show that it does charge. So we're going to turn this back to 0. And look, 1.61, 1.60. See? Pull that out. It had to put more voltage in to counteract what was already in there. So let's hook up our meter. So the meter, the negative to... Don't confuse your power supply cables and your meter cables. Should be obvious what might happen then. Put your positive, no, this is the negative. Black is negative. Put negative in negative. Positive in positive. And you will see the battery is now putting out 1.605 volts, according to this multimeter. Again, it's all rough. The way the multimeter measures voltage, this is not a short circuit. It's just a resistor inside the multimeter that's limiting current, and it measures the voltage across the resistor and flips it. The only time you have to worry about a short circuit is if you're measuring current. If you're measuring current, it's not got a resistor in there, so be careful. And if you're measuring resistance, there shouldn't be any power at all, because it's going to supply power. But voltage, just plug it in, is perfectly fine. It uses its own resistor. So now you've seen that you can recharge an alkaline battery. But as I said, you really shouldn't. It's just not necessary, it's not economical. If you're trying to save money, the amount of money you'll save is not worth the headache. And if you're not very good at what you're doing, you won't save money because you'll screw things up, you'll waste supplies, your batteries will explode, and then you can't recharge them. Batteries that are completely depleted shouldn't be recharged because they are incredibly likely to blow. So it's just not worth it. If you're trying to be green, if you're trying to be environmental, buy rechargeable batteries in the first place. Get yourself a solar cell. If all you're doing is charging batteries, you don't even need it on your roof. Just get one and hang it outside on the south side of your building, or if you're in the other half of the world, on the north side of your building, right out your window or something. You know, take it in when it rains. And you can charge your batteries off of that, and you'll use the same 8 AAA batteries for 25 years, if you're careful. So, there you go. Like I said, the only reason to do this is to have fun, and to understand the chemical reaction, the reversible chemical reaction, power supplies, multimeters, breadboards, all of this stuff. It's a great learning experience, although it's much easier to watch a video and not risk having to clean white powder chemical off of your table. Just remember, wear your eye protection just in case, because that's the only part of your body that's really vulnerable. Well, that and your mouth. You could breathe it in, but then it's like, go drink a bunch of water, you'll be fine. It'll just dilute it. If you get it on your table or whatever, get a wet cloth, wipe it up. If it's on your hands or any other part of your body, wash your hands, rinse your hands, take a shower, whatever. It's not going to hurt you, as long as you don't leave it on there. So, don't worry. Just put on some sunglasses, you'll be fine. So that about does it. Remember to give your daily genuflection to the spirit of our good friend Maxwell, and be seeing you.